What would happen if every single person on Earth aimed a laser pointer at the moon at the exact same time? Would it change color? Well, not if we use regular laser pointers. First, consider the visibility issue. Not everyone on Earth can see the moon at once. We could theoretically gather everyone in a single location, but history has shown us that's not a great idea. Still, most of the world's population lives between 0 and 120 degrees east, so our best chance would be to try this when the moon is positioned over the Arabian Sea. Now we choose a quarter moon phase observed at night, so we can compare how the lasers affect both the lit and dark sides of the moon. A typical red laser pointer has a power of about 5 milliwatts. A high-quality one can produce a tight enough beam to reach the moon, but by the time it gets there, the beam would have spread out, covering a significant portion of the surface. Let's assume, for argument's sake, that everyone's aim is perfect and the light from all the lasers spreads evenly across the lunar surface. Here's what happens: nothing. And that's not surprising. Sunlight hits the moon with over 1 kilowatt of energy per square meter. Given that the moon's cross-sectional area is about 10 trillion square meters, the summit half of the moon receives around 6 petawatts of power. In contrast, the combined output of 5 milliwatt lasers from every human on Earth would add up to just about 30 megawatts. That's roughly 200 million times less powerful than the sunlight already hitting the moon. In other words, the laser effect would be completely drowned out. But what if we ramp up the power? Let's say instead of 5 milliwatt lasers, we give everyone a 1 watt laser. That might not sound like much, but a 1 watt laser is no joke. It's dangerously powerful, capable of causing permanent eye damage, burning skin, and even starting fires. These aren't your average laser pointers. In fact, due to safety regulations in many countries, they're often sold under code names like blue flashlights online. Suppose we somehow spend $1 trillion to provide every person on Earth with a 1 watt laser. What then? Well, the collective lasers would illuminate the moon with around half a lux. That's about half the brightness of typical moonlight as seen from Earth. But remember, the moon is still being blasted with 130,000 lux of sunlight. Our lasers are still insignificant by comparison. Let's go further. Forget lasers. Now, we hand out night suns to everyone, massive searchlights used by law enforcement, and Coast Guard helicopters. Each one puts out about 50,000 lumens, powerful enough to turn night into day over a small area. But to target the moon, we need to add lenses to focus the wide beam down to half a degree, which is about the angular width of the moon in the sky. It's subtle, but we're making progress. Our combined light output is now generating about 20 lux on the lunar surface, which actually outshines the ambient light on the moon's night side by a factor of 2. Still, the illuminated side remains completely unaffected. More power then? Let's upgrade again. Swap each night sun for an IMAX projector, powered by 30,000 watt lamps that produce over 1 million lumens. Theoretically, this gives us a better shot, but even then, the light barely makes a dent. It's still nearly invisible against the harsh glare of the sun. Okay, one last attempt. Atop the Luxor Hotel in Las Vegas sits one of the world's most powerful spotlights. Let's take that light, equip it with a focusing lens and a colored filter, and give one to every person on Earth. Now we're talking. The focus beam, with its intense output and unified color, finally makes a difference. Our light becomes visible from Earth, bouncing off the moon with just enough intensity to be seen. It's faint, subtle, but it's there. A glimmer of artificial light, reaching across space, unified in color and purpose. We finally left a visible mark, no matter how faint, on the moon.